Thank you. Hello, everyone, and welcome to An Introduction to Quantum Computing webinar by Mr. Doug Finke here at Aggregate Intellect. My name is Reza, and I organize the quantum technology stream here at the Aggregate Intellect. I'm very excited to host Doug Finke from the Quantum Computing Report today. In this presentation, Doug will describe some of the basic quantum physics principles important in welcome to an introduction describe the various implementation of technologies that are available to construct a quantum computer, why a quantum computer can provide a performance advantage over a classical computer, the different types of quantum computers, what applications may be suitable for quantum computers, and some of the major players that are providing quantum computing hardware and software. If you have any questions, please post them in the chat box in our YouTube channel, and I will ask Doug at the end of this webinar. Doug has been involved in the quantum computer, semiconductor, and storage industry for over 30 years at companies including IBM, Intellect, Corning, Western Digital, and several startups, and has witnessed and helped drive the birth and growth of many new technologies during this period. He has most recently become fascinated with the quantum computing and believes that many of the new technology growth patterns he has seen within the computer industry will reoccur as the quantum computing field evolves. He started the Quantum Computing Report so he could apply his wide breadth of experience to help accelerate and proliferation of quantum computing to the general marketplace. He is also a member of the World Economic Forum Global Future Council on Quantum Computing. Doug holds degrees in computer engineering and management from the University of Illinois and MIT, respectively, and can be reached at dogfinke@quantumcomputingreport.com. Thank you so much for being here and giving us this time, Doug.
Okay, you're welcome, Reza, and thank you for the introduction. Let me get my presentation on the screen now. Give me a second.
Sure. Thank you very much.
Okay, and put it in full screen mode. Okay, hope everyone can see this now. So I will talk about an introduction to quantum computing. I'll talk about some of the basic physics concepts, where it could be used, and who some of the players are. And then we'll talk about what I think will happen with the initial deployment. So quantum computing is really based on three physical principles that really were not discovered until the 1920s and 1930s by guys like Albert Einstein, Heisenberg, Bohr, and several others. It was sort of a new branch of quantum physics. And it's very non-intuitive. The very famous scientist Richard Feynman has a fun quote we like to say, which is, if you think you understand quantum mechanics, you do not understand quantum mechanics, because it's much different than what we normally see in our day-to-day lives. But the three principles that I think are key are tunneling, entanglement, and superposition, and I will explain what each of those are in the following slides. So tunneling is important for a branch of quantum computing called quantum annealing. There's a company. You can't see the slides. Let me start share again. Hold on. Let me start again. And okay, can you see it now?
Not yet, Doug.
Okay, hold on.
You may want to hit that present now button. And
yeah, and
wonderful.
How about now?
Yes, we can see it.
Okay, very good. So talk about tunneling. Tunneling is a concept where you can take either a state or an electron and have it tunnel through a barrier. And this shows, for example, a hill. You want to get this boulder over the hill. The classical way of doing it is you have to roll it up, go over the hill, and go down. But in tunneling, you can go right through the hill. And this is actually very important in classical computing. It's in flash memories, which make use of this concept. Um, and that's relatively recent within the past 30 years. But tunneling is used for quantum annealing. The second effect is entanglement. And entanglement is something where Albert Einstein called it spooky action at a distance, where basically you can take two particles and they're linked together such that if you do an action on one of them, it will affect what's happening on the other one, even though that the other one could be miles or even worlds away. It happens instantaneously, and that's actually one of the keys to something for unbreakable quantum key distribution that is used. But entanglement is also very important for quantum computing. And then the other is superposition. So in the classical world, we're used to bits. Bits can be in the 0 or 1 state. In quantum computing, they use something called a qubit, which is either a state or sometimes a particle where it can be at both simultaneously, superposition of those. And this could be manifested in a number of different ways. In a superconducting circuit, you could have a loop of wire, and you could have currents flowing both clockwise and counterclockwise at the same time. In an electron, you can have what's called spin up and spin down, and at that time, it could sort of be in both at the same time. But superposition is also very important. It's one of the things that gives quantum computing its power. And talk a little bit more about qubits. There are several issues with it, or things that make them not all that easy to work with, which is why quantum computing is hard. The first is called decoherence. You know, I showed earlier the fact that think of this one on the right as a coin that's in 0 and 1, and maybe it's spinning, you know, around, round and round, 0 and 1. But after some time, the qubit will collapse and it will fall back to either 0 or possibly the 1 state. And that is called, the collapsing is called decoherence. And depending on your technology, the qubit can only stay in that superposition state, could be anywhere from 50 microseconds to several seconds, but it ultimately will collapse. Also, I should say it's, although you think about superposition where essentially the 0 and 1 are in like a 50-50 state, it actually can be any mixture of that. It could be 30-70, 20-80, 80-20, that type of thing. But the really strange thing about qubits is that if you measure them, if you observe them, then they will collapse immediately. So you may have heard of Schrodinger's cat, which is both alive and dead at the same time. But once you lift the lid on that box and look at the state of the cat, he's either going to be one or the other. And that's one of the things that makes quantum computing hard. Another thing that makes quantum computing hard is what's called the no cloning theory. You know, in a classical computer, I used to design hardware at one point. It was very common that you'd have a bit and that you would just run it through a buffer and you make multiple copies of that bit. You can't do that exactly in a quantum computer. So it creates some issues, and you have to figure out ways to work around it. So there are a lot of technologies to implement qubits, and I'll show those on some of the following slides. But things that people look at when they look at an implementation, they look at the number of qubits, the coherence time of the qubits, what the delays are to implement gates, What's called the fidelity is how accurate those gates are. How often do they give you the right answer? And of course, the connectivity to other qubits. And I'll show that. And connectivity is shown here, where actually shown here, where um, it's basically how the qubits talk to each other. In this case, qubit number 5 can only talk to number 3. It can't talk to number 1, 2, or 4 directly, versus this type of technology, qubit 5 can talk to each of the other qubits. So if you're implementing a quantum program, the one on the right is actually better, all else being equal. Now, one of the interesting things about quantum computing is that there's several different technologies, ways you can implement that, from superconducting, trapped ions, quantum dots, topological qubits, photonics, and those types of things. And different companies are pursuing different approaches. So it's like the early days of semiconductors, in my opinion, where there were many different semiconductor technologies, and ultimately one became dominant, but it took about 50 years for silicon CMOS become dominant. Right now, the current leaders are superconducting technologies with IBM, Google, Rigetti, and others developing superconducting technologies. Trapped ions is an up and comer. Companies like IonQ and Honeywell and AQT are doing that. Intel is working on quantum dots. Microsoft is working on topological qubits. And then there's photonics too. People are using photons in various states, various polarizations to represent qubits. And all these are in competition with each other to see which one's going to be the leader or become dominant. But it's going to take probably a couple decades to really determine that. Superconducting and silicon quantum dots are the ones that are probably the most compatible with semiconductor manufacturing technologies. That's one of the reasons why people use them. And Intel, for example, is an example where they're leveraging one of their high volume fab facilities in Oregon to build their quantum qubits. So qubits are very, very fragile. As I indicated before, they collapse, they decohere very, very quickly. And people go to extraordinary means to try to extend these as much as possible. One of the technologies, and you'll see this in almost any presentation on quantum computing, is this device called a dilution refrigerator, where if you have a superconducting circuit and you keep it at a very, very cold temperature, and 15 millikelvin degrees above absolute zero, that will help minimize the external disturbances that will cause the qubit to collapse and have premature decoherence. So these are very expensive devices, by the way. These dilution refrigerators, they cost about $700,000 roughly, but you can see it here where it goes through stages where it starts at, of course, at room temperature, which is 23 degrees. I'm sorry, 273 degrees Kelvin, and in various stages it cools things down to very, very low temperatures. But besides of trying to minimize the temperature, these devices are also placed in vibration-free housings under, of course, vacuum, a lot of magnetic and RF field shielding too. So these are, again, some of the challenges that the technologists have to implement these things. I will point out that superconducting, that these dilution refrigerators are not required for photonic or ion trap technologies. Those technologies are not quite as sensitive to temperature, although they may be sensitive to other things like vibrations. But this is a major component in the superconducting quantum computers. So now I'm going to talk about two major types of quantum computers. They're called, well, first is called a gate level, and the second is called adiabatic quantum annealing, which is promoted by a company called D-Wave in Vancouver, Canada. First, talk about gate level. If you're at all familiar with classical computing is all based on digital logic gates, as you see on the left, NAND gates and NOR gates and inverters, those types of things. And those are basically specified by truth tables, as you can see here. There's something similar in the quantum world. They're called quantum gates. And some of them are similar to what we see in classical computing, like a NAND gate is similar to the NOT gate in a classical computer. If you look at diagrams, these are how these are typically represented with boxes. The top three are all called single qubit gates, and basically they take a qubit and they manipulate it somehow in terms of the state it's in. I won't go into it in this presentation, but there's something called a block sphere, and the position on the block sphere can represent the state of the qubit, and these gates here can change where it's located on the block sphere. But these are all 1 qubit gates. The second type of gate is called a 2 qubit gate. In this case, it's a C0, very similar to an exclusive OR, where this is the control qubit, and whether or not, if the control qubit is 1, it'll invert the state of the bottom qubit, which is called the target. But you can specify the operations of these mathematically with matrix. So a lot of the qubit algorithms, the quantum algorithms, can all be specified mathematically using linear algebra and matrices instead of truth tables here, which would use Boolean logic. Now, to show how this would work, and why, one of the reasons why there's some power in a quantum computer is the way I say it's sort of a weird form of parallelism. So in a classical computer, if you want to do a number of different operations, in this case, maybe it's an addition or something like that, and you want to add a set of different numbers, you have to put in those numbers sequentially, and you'll get the output sequentially. In a quantum computer, what you can do is you can take advantage of that entanglement state where all the qubits are put in that 0 and 1 superposition. You could fit it into the logic composing of those quantum gates I was showing before, and you'll get all the answers out at the same time. And this is one of the reasons that you can get some speed ups. So the way you have to look at these, and you'll see these quite often in charts, is if you have 4 qubits, you can do the mathematical algorithms such that the outputs will appear in different probabilities. If you measure this, if you repeat this operation, let's say 1,000 times, you'll get a distribution of what the outputs are. These are the values here, and these are the probabilities of achieving that. And I'll show you, for example, how something called Grover's algorithm takes advantage of that to do that. So quantum computing is really a probabilistic in nature, and many of the implementations you see, and in fact all the implementations you see, will run a quantum circuit, but they'll do it perhaps 1,000 times or 10,000 times, and those are commonly called shots, so that you can see the probability of what the output is, and typically the answer is the one with the highest probability. So Grover's algorithm is an example of how it's done. Grover's algorithm is a search algorithm. So you search for a number in a list. If, for example, you have a list, let's say it's 1 trillion items long, 10 to the 12th, you basically, and it's an unordered list, typically you'll have to search through, worst case, you'll have to search through all trillion until you find a match. Probabilistically, you'll get lucky, and roughly about 50%, about halfway through, you'll be able to find the match. But in quantum computing, with Grover's algorithm, you can do that much faster. Basically, it's a square root of a trillion, or basically just a million times. And that's, again, a demonstration of the speed up. So the way it works is a quantum state. Almost all the algorithms start. You take your input qubits and you put them in an equal probability. Again, the superposition of 0 and 1, and these are at the 50-50 state. You run it through a circuit, in what's called in the literature an oracle, where the one that matches is just flipped. And you can have, and again, you have to go through the mathematics, but you can have negative values for the state of a qubit. And then you do something called invert around a mean. And if you look at it, what will happen is the ones that are in the positive state are reduced because it's influenced by this negative, but because this is inverted, this gets positive. And you repeat that over and over again, and essentially the one where the matches will ultimately come very, very close to 100% probability. So that's a quick overview of Grover's algorithm. And again, the typical search time is about n over 2, where n is the number of items in the list. But it's a square root of that if you do it quantumly. Here's another algorithm. It's called Shor's algorithm, and this chart is actually quite important. One of the things that computer scientists look at when they look at algorithms in general is how they scale up. And the term that the computer scientists use is called big O notation, where the search that I just talked about, basically, if you have a list that's, let's say, 1,000 items long and a list that's 2,000 items long, the second one, 2,000 items long, it will take twice as long. And that's a scaling factor of n. But there are other algorithms where the scaling factor might be n squared or n cubed. There might be things where it's 2 to the n in terms of, n is sort of when I say 2 to the n, it's the number of operations needed to perform that algorithm. One of the applications that I'll show later on is called the traveling salesman problem, where at least one of the algorithms that's used, called the brute force search, is n factorial. And if you try to solve that in a classical computer for a problem where you have a salesman going through 100 cities, it's roughly 10 to the 127th operations you would need to do before you find the optimum path. So what the computer scientists do, they plot these, the number of n versus the time to solution.
Mm-hmm.
And if there's one thing that you keep in your mind in terms of why quantum computing works, what I would say is what it does, it cuts down the slope of this line. The black line would show a factoring problem, and how it would be solved in a classical computer versus the number of bits. And you can see this slope is very, very steep. Quantum computers, though, the slope is much, much more, it's still not quite linear, but it's much, much shallower. And that's really the secret of quantum computing, is if you can do, everything you can do in a classical computer, you can do in a quantum computer. But for some algorithms, there are some algorithms where the quantum algorithm just will scale up a lot less rapidly than you can with a classical computer. And this is really where the power is. For example, quantum chemistry, the scaling is also exponential with the number of atoms of the compound or the molecule you're trying to simulate. It's not quite that bad. in quantum computing, and that's where the real power is. But it also points out that you sort of need a certain level. At low levels, if you're only doing factoring of 100-digit number, then actually classical computing is better than quantum computing. But when you get into the thousands of qubits, that's where the quantum computing wins out. So there are a couple terms that I'd like to define. At the end of the day, the reason everyone's investing money in quantum computing is that it can do something better than a classical computer. If it can't do better than a classical computer, then you shouldn't be working on it. You shouldn't be spending money on it. But there's a bunch of terms that are thrown around that I would like to define. One is called quantum supremacy. This was defined by a Caltech physicist, Dr. John Preskill, where was a situation where you can have a problem and you find a quantum solution to that problem, and it's either faster or higher quality than what can be achieved by a classical computer. And about a year and a half ago, Google made news. They had a made-up problem. It's not a real-world problem. It's called I think they call it a crafted problem, where they found something where they thought a quantum computer might have an advantage, and they demonstrated that. They write a very nice paper in Nature magazine, and they showed that their quantum computer, which they called Sycamore, was able to do that faster than the fastest existing classical computer that was at Lawrence Livermore National Labs, called the Summit classical computer. And they got a lot of press for that, but the point, some people said that's an interesting thing, but it's not a real world problem. You can't really use that for anything of high value. But it's a stepping stone. And the next thing that I think you'll see, and you may see that within the next year or two, is some people doing something similar for a commercially or scientifically relevant problem. And that's really where the payoff is, where you can do something that is important, like simulating a chemical module, computational chemistry, or doing a finance optimization problem where you're doing some portfolio optimization, and you can use a quantum computer and it provides a better result or a faster result than what you can get with a classical computer. So you need a certain size of quantum computer to do that. One thing to remember is that I can write a quantum program with a small number of qubits, 20 or 30 or 40 qubits, and there are programs that allow me just to simulate the operation of a quantum computer on a classical computer. I could simulate it, for example, a 20 qubit quantum computer. I can simulate that on my laptop. So the people say that these problems that to achieve quantum advantage, you need at least 50 qubits, because the simulation is one of those things that increases exponentially with the number of qubits. So, for example, if you are barely able to do a 50 qubit simulation, just by adding one more qubit, going to 51 qubits, you basically will double the amount of time required for the simulation. You go to 52 qubits, it's 4 times. So it increases very, very rapidly. So people say that roughly 50 qubits would be the limit with regards to what you could simulate. Okay, let me talk about quantum annealing, because this is a different thing. This was really pioneered by a company called D-Wave. As I was saying before, one of the things that is quite common in many, many problems in physics and optimizations and logistics is you're trying to optimize something. You're trying to find what physicists would call the lowest energy state.
Mhm.
In a traveling salesman problem, for example, you want to minimize the number of miles that the salesman will do. In a portfolio analysis, you might want to maximize something called the Sharpe ratio, which is the ratio between risk and reward. various logistics. If you're routing traffic, for example, you want to minimize the wait time or the traffic convention. So these problems can all be expressed mathematically, and depending on the various parameters you choose, you'll get a different energy level or optimization level. And the trick is to find the one that is at the lowest level. So, this has been used in classical computing for many, many years. And one of the most popular techniques for this is called simulated annealing, where people will try out different things until they find the lowest things. The problem is that some of these classical technologies will get trapped in what's called a local minimum. If the ball is right here, as you can see in this upper left, um, it may say, hey, I can't go right because that increases my energy level, and I can't go left because that increases my level. But it didn't realize that if it was able to go somehow tunnel through this hill, it can get to the lower level. But if you take advantage of quantum tunneling, you can do exactly that. And that's really what the D-Wave computer will take advantage of. Again, the D-Wave computer, it's based on superconducting technology where you have circuits that are flowing through the rings. These create a magnetic field, which are up or down, and it can be it starts in a state which is simultaneously. And the lowest energy state ultimately will allow the qubit to settle in the state, in either the 0 or the 1 state, where it has the lowest energy. So this is mathematically, this is called a Hamiltonian, where each one of these thetas is the qubit state, and the H's and the J's are the things that you can program in to represent your problem. So these would create the energy landscape, and then the D-Wave machine will find the theta sub J's and K's that will give you the lowest state, the lowest energy. So here's some examples of how these qubits are connected. This is actually one of the earlier machines where they put the qubits in local clusters of 8, and then they had multiple of these, or they call them tiles. Then they had these tiles connected together. Their latest machine, which they just really announced last year, is called the D-Wave Advantage, and it has over 5,000 qubits. And it's all based on chips, semiconductor-like technology, and this is an example of their chip. They build these chips in a wafer fab, just like semiconductors. This is some of the equipment that you would find in a wafer fab. And the cost of the machine is $15 million. Again, a good chunk of that $15 million is that dilution refrigerator I talked before, but it's very, very expensive, and most usage right now are actually through the cloud. So rather than giving each customer or selling each customer a $15 million machine, they have a few customers who have bought that, but most of them, D-Wave has their own cloud computing capability at their headquarters outside of Vancouver, and people can, over the internet, they can log in and buy time on that machine. But the D-Wave Advantage machine, as I said, had over 5,000 qubits. It has the most complicated Josephson junction design of anything in the world, over 1 million Josephson junction. But the other thing that is important for quantum computing, particularly if you look at the superconducting world, and it's not really appreciated, is the power savings you can have. You may have seen these big pictures of these big data centers at Amazon or Microsoft that have thousands and thousands of classical servers all networked together, but those data centers can take up to 2.5 megawatts. And the quantum computing only takes about 25 kilowatts, and that's mostly for the dilution refrigerator. So one of the advantages in the future that we see for quantum computing is the fact that it's more power efficient. And as people talk more and more and think about a green economy, that's a big savings. Okay, some applications. Yeah, talk about the traveling salesman problem. And again, this is what it looks like. How does this guy go to all these various cities and minimize the number of miles? And this is, it's commonly taught in computer science classes, but uh, the one algorithm is just you have to try out everything, every possible combination. And again, if it's 100 cities, it's n factorial because you have to. It's 100 times 99 times 98 just to try out everything, and this becomes just way too long. It takes billions of years when you have a large n. But because of superposition, because of some of the new algorithms that people have come up with, they are able to solve these in much faster time. Other applications, one of the things that people are working on very hard is called computational chemistry. We're all hearing about COVID and COVID vaccines and how you can design a COVID vaccine. Right now, people have been using classical computing, and but the way a lot of the drug manufacturers, as well as material manufacturers, another similar problem is coming up with battery chemistries, is really through the trial and error process. You just have to take a guess as to what might work, but then you have to try it out. And if you could simulate exactly how it would perform, the way, for example, people designing airplanes can use a wind tunnel or computer simulations to simulate the airflow over a wing, you could design things a lot faster. There's machine learning, various clustering, finding patterns, those types of things. Finance community is very eager. There's something like 12 of the biggest finance companies have set up quantum groups to be able to do things like risk analysis, credit card fraud detection, portfolio optimization, a bunch of other things. Logistics and scheduling. If you're Federal Express and you're trying to route your airplanes for your traffic, what's the best way to do it? I mentioned drug design, cybersecurity. The one that got people's attention was code breaking with this Shor's algorithm. But there are other things that you might not think about are things like fault simulation in electronic circuit. A company like Northrop, which makes airplanes, military aircraft, those have a lot of electronics, and they want to know what happens if there's a fault. But again, those problems can increase exponentially, so that they've used quantum computing to help them solve those types of problems. And so I talked about computational chemistry. You really want to be able to simulate these things, and if you can do that, you are able to come up with new materials and new processes a lot faster. One of the things that people talk a lot about is creating ammonia-based fertilizer from nitrogen in the air. It turns out, this is very important because fertilizer is used for food. We're feeding the world's population. And the process that people are using right now to make this fertilizer is called the Haber-Bosch process, where you take nitrogen from the air and you compress it at very high pressures and very high temperatures, and that will cause a chemical reaction that will create the fertilizer ammonia, NH3. But it turns out that process uses something like 3 to 6% of the world's natural gas. It's really a giant user of carbon-based energy. And it turns out plants can do that without using natural gas, but we don't know how to do it. So scientists believe that if we could come up with a secret formula, the right catalysts, we could be able to replace the Haber-Bosch process with something that's much more efficient. and would save billions of dollars and save, an appreciable amount of the natural gas that's produced yearly. High temperature superconducting materials, of course, is something that people are always looking for. Battery chemistries for cars, for electric cars. Carbon sequestration is another one. Capture carbon from the atmosphere. If someone could come up with a efficient process for this, they could solve the climate change problem. So, what was suggested by Richard Feynman, the guy I mentioned in the beginning, he basically said, look, these chemical reactions are quantum mechanical in nature. Why don't use a quantum computer to simulate them? And that's really one of the things he said that I think in 1981, and that started people thinking about could they develop a quantum computer. Machine learning is another one. One that people do a lot of research on is called the restricted Boltzmann machine. I think this is an AI group, so you're probably familiar with this. But to be able to find the links and the optimization, this is an area where people are researching how quantum computers can more efficiently solve various AI problems. This is still, I would say, in the early stages. Part of the issue is the fact that AI itself is still in the early stages. Many of the AI applications we have right now, people don't necessarily have a real strong theoretical understanding of how they work. They just try it out and something works. So it's hard to translate something like that into figuring out how quantum can do it better. But there's a lot of research in this area. And although I don't think it will be the first application, I think it will be a strong application in the decades ahead. Finance is a big one. Because there's a lot of money involved. If you're a portfolio manager and you have $1 billion portfolio and you can use a quantum computer to, let's say, increase your average return from 5% to 6%, may not sound like that 1% is a lot, but when you multiply it by $1 billion, it really is. So as I mentioned, a lot of the finance companies are looking at this terms of how they can optimize portfolios, arbitrage, credit scoring, fraud detection. Those are things. This is an example of figuring out ways of solving an optimal arbitrage situation. And there's a whole website called Quantum for Quants that is dedicated to these types of applications. Logistics and scheduling. This is used on, this is a daily problem. Any of the companies that have to optimize fleets, whether it's deliveries for Amazon, scheduling airplanes for United Airlines, American Airlines, or any of the airlines, optimizing traffic, a lot of work done in optimizing traffic to minimize traffic jams, optimizing machine utilization in a wafer fab. Lots of applications, and there's a lot of work being done on logistics and scheduling. There was an example where D-Wave and Volkswagen worked together, and basically they did a paper analysis of taxi cabs in Beijing that were taking people to the airport. There were multiple paths, multiple streets that they could take. And of course, you might think that if everyone took the shortest route, that not be good because it would create a traffic jam on that shortest route. But if you could spread it out over other things, let's say there are multiple routes, some are longer, you send some of the cabs over the longer route, but overall it would reduce the travel time for everyone. So they've done a lot of work on that, and they're continuing to do work. This could indeed also be, or something similar to this could be one of the early applications of quantum computing to reduce traffic jams and travel times on the highways of a city. So cryptography gets a lot of press right now. The thing that got people excited was the fact that today's cryptography is based on a problem of how do you factor a large number. Factoring is one of those, it's called a one-way problem. If I have a pair, two prime numbers, each of them is 1,000 bits long, it's very easy for a computer to take number one, 1,000 bits, multiply it by number two, and create roughly a 2,000 bit number. But doing the opposite is very, very difficult. Taking a 2,000 bit number and breaking it down into those two original prime numbers, if you don't know them, is computationally extremely hard and would take billions of years on even the largest of classical computers. So in 1995, a scientist by the name of Peter Shor figured out how to do that. If he had a large enough quantum computer, and we're talking about a quantum computer that maybe has 4 million qubits, he figured out an algorithm that would be able to do that in just a matter of hours on a quantum computer instead of billions of hours. So that got people thinking about it, and not only thinking about how they could develop quantum computers, but how they could protect against this. And what's happening is there are two different ways of solving this problem. The first way is to use quantum mechanics and the entanglement that I said before, and using things like the no cloning theorem I had mentioned previously, where you could come up with a proof of a way of sending data from the sender to the receiver without and be assured just through the laws of quantum mechanics that it's not scrambled. China has demonstrated that over over a satellite. Most of the systems actually send those through fiber optic cables. The other approach is just to come up with new classical algorithms that are not dependent upon factoring. The U.S. agency NIST, National Institute of Standards and Technologies, has been running a competition for the past several years to come up with these. And there are several algorithms that are being shown that people have not been able to break with a classical quantum computer. So we do believe that they will select one over the next couple of years, and there will be a gradual migration in terms of security for the internet based on, which is today using RSA or similar types of older things based on these one-way problems, and coming and converting to these newer methods, either the software-based approach with these new algorithms, or the quantum approach in fiber optics using the entanglement principle. So, the question is, how many qubits do you need to solve a problem? This is an estimate that Microsoft provided at one point with regards to various problems. I talked about nitrogen fixation. They believe if they had a solid 100 to 200 qubit computer, they could do the simulations needed to be able to solve this problem. Carbon capture might be something in the 300 qubits. Material science, this is supposed to represent an electrical grid to send out current over superconducting wires, and superconducting wires would have no loss. That would make these much more efficient. Probably need something in the hundreds of thousands, and then machine learning would require quantum computers in the thousands of qubits, and these would all be what I would call logical qubits. Here's what we are today. This is a list I keep on the Quantum Computing Report of where people are. IBM has this online, a 65 qubit online. Rigetti has theirs is at 32 qubits. IonQ has a 32 qubit available, and various others are working on various other types of approaches. Again, many different types of approaches, different technologies. I mentioned earlier superconducting and ion trap were probably the leaders, but you have a bunch of other things. And one of the things that people could happen is that one of these dark horses, like the photonic qubits from a company like Xanadu, could come out from the back of the pack and have a breakthrough and be able to break over these things. So that's what makes watching this technology so interesting. Is at the end of the day, we don't know which one's going to win yet, but and it's like a horse race. You know, it may change. You know, every month or every few years, it may change. So finally, sort of to finish, you know, my portion of the presentation, in terms of investments, this is something that shows about $22 billion have been invested in quantum computing by governments over the past few years. These are some of the leading players: D-Wave, IBM, Google, Microsoft, and Intel. You know, the big players in classical computing are working on this. But there's also a very well-established group of startups. I track over 200 different startups. Some of the more well-known ones are Rigetti in Berkeley, California, INQ, Silicon Quantum Computing in Australia. There's several in Europe. These are hardware players. We have software players, QCware, OneQubit, and others. They're developing algorithms that run on this hardware. People providing various platforms and other programming environments. And in terms of the deployment, the point that I want to make here is that you have to put a lot of different things together. It's not just building the qubits that you have to put together. You have to figure out how to interconnect them. You have to figure out how to control them. You have to figure out how to organize them, program them, create libraries, and use complexity theory to be able to solve, to provide a good solution for the end user. But it's a very dynamic industry, a very robust industry. There are players at each one of these levels. I actually have another presentation I give called Tour Through the Quantum Ecosystem, where I walk through this a little bit more detail, but that's another hour. But what you'll see is a lot of the implementations, and we have a lot of availability that's happening right now is through the cloud. Most of quantum computing will be quantum computing through the cloud. People will access over the internet. You have company D-Wave, IBM, Microsoft, Amazon. All these companies are currently offering a cloud-based access to their machine. And for now, that seems to be the way that most people will use it rather than on-premise, with the only exception of perhaps some government installations that might want to spend that $15 million and buy a quantum computer just for security reasons. So to summarize, quantum computing is coming, but it's important to understand that quantum computing will never replace classical computers. They'll all really be used as a coprocessor, much the same way as a GPU is a coprocessor to a classical computer. And they won't be used for everything. There are only certain problems where a quantum computer is useful for things like Excel spreadsheets or browsing the web or email or balancing your bank accounts. They will never be used. Classical computers will always be superior. The hardware challenges are very, very substantial, but people are starting to overcome them. Software requires completely new algorithms. You just can't, in the classical computing world, if you have a program that runs on an Intel processor and AMD comes up with their own processor that's 2 times faster, you can just move it over and within a day you can have it running on the AMD processor twice as fast. You can't do that. The software has to be completely changed in quantum. And that's one of the reasons why it takes a while to get these things together. But the technology is moving fast, and it's exciting to watch it. So thank you for listening to the presentation. I do have a website. It's called the Quantum Computing Report. You can also contact me by email. But if you're interested in learning more, you can go to my website. We put out news roughly on a daily basis. And I also put out a newsletter that you can sign up for that will show you on a weekly basis sort of the things that have happened. So with that, that's the end of my presentation, and I'll open it up for questions now.
Thank you, Doug. Thank you so much. This is really amazing how much great, up to date, and hands on information distilled in 1 hour talk. I really, really appreciate it. This can be used as, as a course distilled in only 1 hour. Thank you for that. I strongly recommend our audience to check Dog's website. It's a great resource if you are interested in learning more about quantum technologies, different aspects. It's a great, great, great online resource, and it is there for free. It covers lots of information about quantum computing and different players and everything. Thank you so much, Doug. And we are open for questions. If you have any question, please post it on our um, YouTube channel in the chat box, and I'd be more than happy to ask them from Doug. My question, Doug, is people are hearing this. It's so exciting. It's brand new, and it's kind of like we are in the early in 40s, 50s when classical computers were coming up, and you witnessed some of those. What skills do you think people should have if they want to get into these quantum technologies, if they are not necessarily physicists? What toolkits they need to have in their skill set to be successfully, being able to get a job in that industry?
Yeah, so one perhaps misconception that people have is you have to have a PhD in physics in order
Mhm.
to work in quantum computing, and that may have been true 3 or 4 years ago, but it's gotten broader. People with a lot of classical skills are needed, but some of the key skills that are very helpful. The first is to understand mathematics, things like linear algebra, complex numbers, trigonometry. Those types of things are very important because many of the quantum algorithms take advantage of that, and to understand how quantum works, it's very, very helpful. I have another presentation, sort of the mathematics behind quantum computing, that talks about that a little bit. So understanding those branches, again, linear algebra, complex numbers, trigonometry are very, very helpful. The other, particularly if you want to program, is to understand Python, just classical Python, because a lot of the quantum programming languages are really extensions of Python.
Mhm.
So if you know Python, then that's going to give you a head start in terms of programming quantum computing. Um, and then beyond that, you can start looking at the algorithms. There's a number of good online courses and a number of low-cost courses put up. Even MIT has courses. IBM is running a 5-month course right now. That IBM is actually free. There's others that cost maybe $400 or so that you can take, and there's others. There's videos. There's a wealth of videos that are online, and I actually track many of those. I have a page on my website called Education,
Mhm.
and if you want to learn more, you can do that. But at the same time, if you're an engineer that's currently working either in hardware or software, a lot of those skills are needed by quantum companies. For example, if you're a microwave engineer, you know a lot about RF technologies. Um, the way that these qubits are controlled is with arbitrary waveform generators that are, generate microwaves. So being able to understand that, could very well get you a job, even if you don't understand how qubits work. The scientist will tell you, I need a square wave, or I need a Gaussian wave or something like that. And you just have to figure out the circuits that will give you that. Similarly, if you're a software person and you understand how to implement connectivity to the internet, you may not understand how a qubit works, but there's a lot of work in terms of setting up these cloud systems. How do you bill even mundane stuff like billing systems or queuing systems, or those types of things, or having two computers talk to each other. All those skills are needed by these companies. And again, I have on my website a job section where people advertise positions, things that are open for, And I've seen cases where many people are filling those positions because they have the specific skill in classical technology, even though they may not be a quantum physicist.
Wonderful. So it's great to know and clarify the point that you don't have to have a PhD in physics to be able to get a job in that industry. There are openings for people with all sorts of backgrounds and experience and skills.
Yep.
Wonderful, wonderful. My other basically fundamental question for you, Doc, is basically you kind of witnessed this part of this growth and in digital or classical computing. How do you compare what we are witnessing in quantum world with that? Are they kind of similar, or do we have some same trend as Moore's law in quantum computing?
Yes, there is, and I do have a posting on my website. I think it's called a relook at Moore's law for quantum computing.
Mm-hmm.
Moore's law, originally expressed in the 1960s, was the fact the number of transistors on a chip is doubling roughly every 12 months. He later extended that to every 18 months, and I think Intel's now said, well, maybe it's now 24 months, but it's still, improving. But similar things are happening in quantum computing. A year ago, state of the art, maybe 2 years ago, state of the art might have been 20 qubits, and
Mm-hmm.
now we're at 65 qubits for IBM, 53 qubits for Google. IBM later this year will come out with 127 qubits. So it is roughly doubling every year. Now, the other thing to remember, though, classical computing is not standing still. I talked earlier about the fact that quantum advantage. Really the goal is to be able to do something better than a classical computer, but it's a bar that's ever increasing. And even though Moore's law is slowing down, there's still a lot of innovation left in the classical computing architecture to go to non-von Neumann architectures like GPUs, neuromorphic computing, more and more clever classical algorithms. So it's something that's increasing, but we do believe that even though it's a moving bar, the quantum computing improvements are improving faster than classical computing. So it will eventually overtake it. Again, only for certain problems. And that's part of the key if you want to implement quantum, the first step is to go through your organization and really try to understand what problems your organization faces where a quantum computer can help, because it can't help everything.
Absolutely, absolutely. It's very specific type of problems that we can apply to this whole quantum computing notion. And in terms of the number of qubits you mentioned, sometimes we hear like even currently companies or startups declare they have way more numbers, like 100 qubits, basically in terms of classical physical qubits based on logical qubits. Can you explain the difference a little bit for us?
Yes. So the numbers that I showed on my table earlier
Mm-hmm.
are physical qubits. These are just what's put together. But as I indicated at the beginning, the qubits are very, very prone to error. One of the things I should mention is this thing called gate fidelity. If I have a simple, it's called an X gate, which is essentially the same as a NOT in classical computing. I put in a 0, I'm supposed to get a 1 out, or I put in a 1, I'm supposed to get a 0 out. The way the qubits are today, depending on the machine, I have another table on this, you may only get the right answer 99% of the time. 1% of the time I put in a 0, I'm expecting a 1, but I get out a 0. I get the wrong answer. So the qubits are very, very prone to error, and there's a whole branch of quantum engineering called quantum error correction, and it's very similar to classical computing, where you can gang together a bunch of qubits. Let's say you take 9 physical qubits, and you can gang them all together such that you can do this NOT that I was just talking about, and even though one qubit may give you the wrong answer, the other 8 qubits give you the right answer, you're able to correct that. And it's very similar to error correction, if you're familiar with that in the classical computing sense. But the only difference is that, number one, there are two differences. Number one, the error rates are much, much higher. Classical computer gates have a fidelity of like 99.9999999% versus a typical quantum qubit is maybe it's 99%. Because of that, then you have to use more correction. And in some implementations, people are talking about a ratio of a what's called a physical to logical ratio of 1,000 to 1 or even 10,000 to 1. That means for every one good logical qubit that you can count on, you need to gang together 1,000 physical qubits and then do the error correction in order to make sure you're going to get the right answer. So there's a lot of research in that. The problem is it requires much, much larger machines. So that's why it's not available right now. People believe that maybe 5 years from now, and that's the target that guys like Google and IBM have, is to be able to start delivering the 1,000 plus qubit machines and start demonstrating and start implementing algorithms that use a lot of this large error correction overhead and utilize some of those circuits for qubits that you can count on.
Mm-hmm. Mm-hmm.
Right now, basically people are coming up with algorithms that don't do that. So you may occasionally hear the term NISQ, N-I-S-Q, which stands for Noisy Intermediate Scale Quantum. And it's basically an approach where you have these machines that do not have error correction, but the software guys are trying to figure out ways of working around it with very clever algorithms that are able to tolerate errors in the software itself.
Wonderful. Yeah, thanks for introducing us to the NISQ concept. There is a interesting paper by John Preskill on NISQ and how we can use quantum computers in NISQ era for audience who are interested to learn more. I have so many other questions, Doc, but we are like 7 minutes past the time. I will ask one question from our audience. Thanks for the talk, Doc, from Dream Phoenix. What do you make of Chinese recent quantum supremacy breakthrough?
Yes, so I had talked earlier about Google demonstrating quantum supremacy. The Chinese, about a month ago, announced the fact that they had done something similar. We actually wrote several articles that you can read on the website where we analyzed it in detail. But there's a big difference between what Google did and what the Chinese did. The Google did theirs on a machine that was reprogrammable. They could come up with different programs and solve different problems. Just the quantum supremacy experiment was just one of the problems. The Chinese experience was not reprogrammable, and that's very, very important. They also came up with a problem that I don't think it had any real world experience or real world value. They set up a series of fiber optical components, fiber optics and mirrors and interferometers and those types of things. And they also showed that they could do that one problem, but they couldn't do any other problems on that. So, they still have a long way to go. I know there's a lot of concern about, let's say, the U.S., maybe U.S. and Canada versus China. I know it makes for good press, but there's a lot of competitors. I would also point out, I just wrote an article about it, that the Europeans are also making great progress too. So there's a lot of competition out there, but competition also means that people are really striving to make progress. And that's one of the reasons I'm optimistic, because there are so many different people trying so many different things. Some of them will fail, but some of them will work. And that's why I think quantum in general has a bright future, but I can't say who it's going to be a bright future for yet.
Exactly. And I guess we have to just wait and see how it will pan out. I believe
Yeah.
that problem was a boson sampling, and the approach was kind of a brute force approach. Thank you so much, Doug. This was great. So much great information, and I really recommend checking Doug's website if you are more interested. Okay, yeah. Uh, from what I heard, that project is from a Chinese university whose primary objective is demonstrate possibilities and secure funding. Okay, well, we are kind of in that mode right now. Thank you so much, Doug, and thank you everyone who could join us live on YouTube or on other channels that this is being broadcast. This was great. Please join us for other meetings. With next meeting, we will have a senior engineer from IonQ, and he's gonna tell us about how ion trapped quantum computing works. Thank you very much. Have a great day, night, depending upon wherever you are. And thank you, Doug, again for
Hey,
this
thank you,
great
Reza. And I
talk.
want to thank all the attendees. I don't see who you are yet, but you're welcome to contact me if you have any further questions. Thank you.
Wonderful.
Bye-bye.
Wonderful.